5.5 Part 2, Theorems about Polynomial Equations. The conjugate root theorem. The first part of the conjugate root theorem says that if a plus the square root of b is a root, then a minus the square root of b is also a root. The second part of the conjugate root theorem says that if a plus bi is a root, then a minus bi is also a root. In example 1, we are going to use the conjugate root theorem to identify the additional roots. So if I give you negative square root of 2 as one of my roots, based on the conjugate root theorem, positive square root of 2 will also be an additional root. If I were to give you 2 minus I as a root, using the conjugate root theorem, you would say that 2 plus I was also a root. Okay, press pause for example 3, and I want you to write the additional root for 5 plus the square root of 3. An additional root for 5 plus the square root of 3 is 5 minus the square root of 3. Press pause again, and I want you to try this last example. Find the additional root for minus 3i. The additional root for minus 3i is going to be positive 3i. In example 5, we are going to construct a polynomial based on the given roots of 2 minus 3i and 8. So every time it says that it is a root, that means x equals 2 minus 3i and x equals 8. Now in this case, since we're given 2 minus 3i, the conjugate root theorem says that 2 plus 3i is also a root. So now, so that we can begin to make the polynomial, we need to bring the 2 and the 3 to the other side with my x. So I have x minus 2 plus 3i equals 0. Same thing here. So I get x minus 2 minus 3i equals 0. And then to bring 8 to the other side, you just subtract it and you get x minus 8 equals 0. Okay, now that they all equal 0, we are going to begin the FOILing process. So x minus 2 plus 3i is going to be multiplied with x minus 2 minus 3i, which is then going to be multiplied by x minus 8. It is easiest for you to start multiplying the conjugates because conjugates make things cancel out. So we're going to start with x times x. That gives us x squared. X times minus 2 gives me minus 2x. X times minus 3i gives me minus 3ix. It doesn't matter what order you write that in, just make sure you have it all. Move on to the next. So negative 2 times x gives me negative 2x. Negative 2 times negative 2 gives me a positive 4. Negative 2 times minus 3i gives me a positive 6i. Last one. 3i times x gives me positive 3ix. 3i times minus 2 gives me negative 6i. And 3i times negative 3i is going to give me negative 9i, and then that's going to be squared. All right, let's see if things cancel out. Positive 3ix and negative 3ix cancel each other out. Positive 6i and negative 6i. So right now I have x squared, negative 2x, minus 2x gives me negative 4x, plus 4, and then I have minus 9i squared. You know that I squared equals negative 1, so negative 9 times negative 1 gives me positive 9, and then you're going to combine that positive 9 with the 4, and that's going to give you x squared minus 4x plus 13. And then, don't forget, you have this x minus 8 that you still need to multiply by. All right, now we're going to keep going. So we have x squared times x, and that gives me x to the third. X squared times minus 8 gives me minus 8x squared. Negative 4x times x gives me negative 4x squared. Negative 4x times negative 8 gives me positive 32x. Okay, then we're going to do 13 times x, and that gives me 13x. And then 13 times minus 8 gives me negative 104. Okay, combine like terms. X cubed. Negative 8x minus 4x gives me negative 12x squared. 32 plus 13 gives me 45x. Bring down the minus 104 and write y equals in front of it so that it's a polynomial function. Press pause, and I want you guys to try practicing writing a polynomial function that has roots of 1 plus 3i and negative 5. When it says it's a root, that means x equals 1 plus 3i, x equals negative 5, and then the conjugate root theorem says that x also equals 1 minus 3i. Okay, bring them all to the same side with the x, so that way we can set it equal to 0. So subtract 1 and subtract 3i, and that gives me x minus 1 minus 3i equals 0. Subtract 1, add 3i, so that gives me x minus 1 plus 3i equals 0. Add 5, and you get x plus 5 equals 0. Put them all in parentheses, and we need to start foiling. Okay, always start with the conjugates first. It makes it easier and things eliminate faster. X times x, x squared, x times minus 1, x times 3i. Okay, negative 1 times x, negative 1 times 1, negative 1 times 3i. Negative 3i times x, negative 3i times negative 1, negative 3i times positive 3i gives me negative 9i squared. Okay, combine like terms, cancel things out. Positive 3ix, negative 3ix, negative 3i, positive 3i. X squared minus 2x plus 1 minus 9, and replace I squared with negative 1. So that's going to make it positive 9 plus 1, which gives me x squared minus 2x plus 10. Don't forget that you have this x plus 5 that you need to bring down, and we need to multiply some more. So x squared times x gives me x to the third. X squared times 5 gives me 5x squared. Negative 2 times x gives me negative 2x squared. Negative 2x times 5 gives me negative 10x. Okay, move on to the last one. 10 times x is positive 10x. 10 times 5 gives me 50. Then we need to combine like terms, and that gives me x cubed. 5 minus 2 gives me 3x squared. 10x, negative 10x goes away. Bring down the plus 50 and write y equals in front of it. Descartes' rule of sine is going to allow us to determine how many positive real roots and how many negative real roots we have. So to determine the positive real roots, we are going to count the number of sign changes between consecutive coefficients. And then it is either that number or is less than that by an even number. The negative real roots is equal to the number of sign changes between consecutive coefficients when you plug in negative x, or is less than that by an even number. In example 7, we're going to use Descartes' rule of sines to help us determine how many positive real roots there are and how many negative real roots there are. Okay, so now let's look at the positive real roots first. So the positive real roots talked about the number of sign changes between consecutive coefficients. So let's determine our number of sign changes first. So all I'm doing is I'm rewriting the polynomial that was given to us. Okay, so between positive 2 to negative 1, the sign changes from positive to negative. Okay. So then from negative 1 to positive 3, again the sign changes from positive to negative. And then from positive 3 to negative 1, the sign changes again from positive to negative. So there is a possibility of there being 3 positive real roots. And then after that, it said, or less than that by an even number. So if you were to take away 2, which is an even number, from 3, that would leave you with 1. So there's either 3 positive real roots or there's 1 positive real root. And the reason why you don't keep going farther than that is you're going to get negative numbers, and there's no such thing as negative positive real roots. Now for us to determine the number of negative real roots, we have to first replace all of our x's with negative x, and then we're going to have to simplify. Okay, so let's start first with the negative x to the 4th power. Any negative number being raised to an even exponent is going to make that become positive again. Okay, negative x to the 3rd power is going to stay negative, but then when you multiply it by that minus sign, it becomes positive again. Negative x squared becomes positive. Remember, any negative number to any even power becomes positive. And then you just bring down the minus 1. All right, now we're going to count the number of sign changes. So I go from positive 2 to positive 1, no sign change. From positive 1 to positive 3, again, no sign changes. All 3 of these are positive so far. And then from positive 3 to negative 1, there is 1 sign change. So I can't subtract 2 because, again, it would take me to a negative number. So I have a possibility of having 1 negative real root and either 3 positive real roots or, again, only 1 positive real root. Press pause and practice writing the number of positive real roots you could have and the number of negative real roots you could have. For the positive real roots, we are just going to count the number of sign changes. So from positive 1 to negative 1 is a sign change. From negative 1 back to a positive is either 2 sign changes or it's 0 sign changes. Now when we go to look at the negative real roots, I have to plug in negative x. Okay, negative x to the 3rd power is going to stay negative x to the 3rd. Negative x squared becomes positive, but that minus sign makes it negative again, and then bring down the positive 1. Okay, so from negative x to the 3rd to negative x to the 2nd, those are both negative, but then from negative x to positive 1 makes there be possibly 1 negative real root.